Imagine we are in the year 1684, the time of Sir Isaac Newton. We are a gathering of philosophers who later will be referred to as theoretical physicists. Hiding in one of the old offices of the Royal Society in London, we share a common goal. We want to get hold of the fundamental laws governing our world. And we wish to express them in the language of mathematics, following the ideas of Galileo Galilei. But how do we go about this? And where to begin? Welcome to the first session of Physics from a researcher's point of view. As we can see, we are immediately confronted with difficult questions right after having stated our ultimate goal. Let's learn some techniques and strategies how we can tackle them. This session is going to be a long one, so get comfy, grab a tea maybe, brains on, and let's go. How do we go about finding the fundamental laws of our world? And where to begin? It is a very complex question, but also very vague. So try breaking it down. Here are some possible strategies you can try out. You can start brainstorming things that need to be done, or the questions we need to answer. Then try putting them into a priority list and go on finding answers starting from the most important question. Another and maybe a more useful technique for such a complex and tricky question is to start with the first idea that comes to mind. That is your anchor and starting point. Now think about this idea more carefully. Is it self-evident, or does it require that you make any further assumptions about the world that need to be justified? You start breaking it down from here using repeated questioning. This is a method that one of the most influential ancient philosophers, Socrates, made popular. Try it out. I recommend you pause the video now and really think about these questions for at least 5 minutes or more. Write down your ideas. Use a mind map to record it. Be careful. You can't use the physics you have learned in school or elsewhere, because we haven't discovered it in 1684 yet. Remember to compare your thoughts against the comments below, as well as the discussions on Discord. This is really not an easy exercise, but I hope it gave you a feeling about the difficulty of the problem and learn one main thing when you start doing research. It's hard to make the first step when you're looking for a path, but only see the vast, dense jungle in front of you. But a journey of 1,000 miles starts with the first step. So let's dive into it. Let's apply the technique of Socratic inquiry I have mentioned before to help us with getting started. Instead of overcomplicating things and getting lost in thought, we just start with the first idea and develop it from here. I have already started the mind map. It contains the ideas that we have been mentioning before. It will help with keeping track and breaking down of my thoughts. So my first idea to get started was to consider the dead stuff around me, like this pen, for example, and understand why it behaves the way it does. How did I get this idea? Well, I was observing the world around me, noticed all the non-living objects, and was hoping that understanding them first will lead me closer to understanding the laws of the world. So let's pop it down. But why only the dead stuff? Isn't the world full of living beings? What about understanding you or me, for example? Are we not part of this world too? Yes. Why should we separate living and dead matter? Give it a quick think. I would say the main reason is complexity. To begin with, a mathematical description of the world we are aiming for will be based on patterns. Looking around us, we see that all the dead matter is basically just lying around, seemingly doing nothing. If we interact with it, like dropping a pen, for example, then something happens. The pen falls. If I repeat it, I can see that it follows the same pattern, more or less. We can study this. If you try to do this to your cat, however, the patterns are much more complicated. Indeed, one of the patterns might be a scratch on your face, as your cat might not like you doing that at all. So don't try it at home. Back to business. I have added this to our mind map. We want to start with the more simple things first, and then move on to the more complex stuff later. But why? Because we do secretly hope that we can explain the more complex stuff in terms of the more simple stuff. In hindsight, this is why we are making the distinction between simple and complex to begin with. But can we really? I guess we will have to try and find out later. Lesson learned. Try to keep things simple and move from simple to more complicated. Look to start with the more simple rather than the complicated stuff first. The questions we are asking are difficult enough. No need to make it harder than it already is. Now let's think about this more carefully, as suggested by our strategy. Hang on. What does it actually mean to be living and dead? Hard question. You might notice that we are just getting started and we already run into big problems that we find hard to give definite answers to. Don't talk about 1684, it's hard even today. So how should we deal with such questions? Should we ignore them? Should we try to answer them? What do you think the best strategy would be here? Pause the video and write down your thoughts. We cannot afford to answer every single question in great detail. We wouldn't get anywhere like that. Compare this to finding a path in a jungle. So we want to get from A to B. Now, imagine we go on this path and we see many interesting side paths and we just start taking them. They might lead us nowhere or might lead us back and maybe even back, so far away from our goal. We will just get lost and confused. What can we do about it? Shall we just ignore all these questions? No, we are explorers. We should take notice of the possible and interesting side path we could take, record them, and maybe explore them later. Yes, such questions and ideas are valuable. We should have a system in place for bookkeeping of ideas we might want to investigate further later. But we have to choose the questions we want to tackle in depth wisely. How should we apply this to the question about distinguishing between dead and living matter from before? We shouldn't simply skip this question, as it is important for us. But we shouldn't attempt to develop a too sophisticated answer either. We need to deal with it effectively. Right, we have a good idea what an alive object is. So let's stick with that intuition for now, rather than trying to answer generally and definitively. Relying on teamwork is a great idea too. We should refer this dead versus life matter problem to other philosopher colleagues. Some of them might be called biologists later. That is 3 lessons learned. Firstly, when breaking down complicated problems, identify the important questions for making progress first and try your best to answer them in depth. Second, have a personal knowledge management system in place to bookkeep tangential questions and ideas for later, or to delegate it to others. Third, research is teamwork. Really? Don't we just learn about all these lone geniuses who advanced our understanding of physics all by themselves, like Albert Einstein? Although this impression is certainly created, it couldn't be further from the truth. Without standing on the shoulders of his predecessors and teachers, Einstein would not be able to arrive at his ideas to begin with. He was very much inspired by the work of philosopher and physicist Ernst Mach, for example. Without having regular discussions with his colleagues and peers, he would not be able to confirm, develop, and sharpen his ideas to proper theories. Without the help of his collaborators, he would not be able to carry out all the necessary work to turn his theories into mature physics and get it published that would convince fellow physicists. In fact, he always relied on and later even employed mathematicians to help him with the many tedious but necessary calculations he had to do. I have left a link for you in the description if you would like to learn more about Einstein's companions, colleagues, and helpers. So yes, research is teamwork. Phew, that is lots to think about, and we digress a little bit. So let's return back to our first point. We shall concern ourselves only with that stuff for the time being. Let's call it simply matter. So I'm going to bracket out the dead, and we will be calling it matter. But what do we mean by world? We really just mean the material world around us in our context. Maybe let's use the word universe instead of world. So is dealing with matter where we begin? Yes. But how should we study that matter? And how can we know that studying matter will give us insights about the fundamental laws of the universe to begin with? Hang on, are we not part of the universe ourselves? Also, are we not relying on our senses to study matter? And those senses, are they not part of the universe themselves? So the universe is able to observe and understand itself? So are we able to discover the fundamental laws at all? Do they even exist? Whew. This barrage of questions surely makes me dizzy. Let's take it one at a time. Indeed, a major obstacle we are confronted with is that we are trying to understand the box while being part of it. The box meaning the universe, of course. This is why we have to ask questions like, what can we know and how can we know? What would we do to deal with this obstacle? Brainstorm some ideas, and as always, check the comments below or on Discord when you are done and join the discussions. I am curious what ideas you have come up with. I think The way to overcome this is to make some fundamental assumptions about the world, which we call postulates. To go back to my analogy with exploring the jungle we are trying to cross, for example, we would certainly believe in the existence of a path through the jungle. So let's imagine this is the jungle and we are here. We surely would believe that the jungle has an end and that there is a possible path. We would also believe that it is possible to find this path and traverse it. That we can do that with the food, water, equipment we have available, and so on. If we do not hold these beliefs, we could not start thinking about crossing the jungle seriously to begin with. Of course, our beliefs might turn out to not agree with reality. For example, once we start exploring a path, we might run into a river that we simply cannot cross. But so what if there are obstacles that make us question our beliefs? We have already made some progress and found a possible path. We are on the journey. Now we need to tackle that obstacle that we could not cross before and overcome it. For example, by going back, getting a ship, or building a raft, you name it. If we hadn't started the journey, we would just think in circles, not arriving at anything, and probably get scared of the jungle, remaining trapped where we are, namely here. So yes, we have to be prepared to reflect and adapt our beliefs when forging our path, because they might not be correct. But that should not hold us back with getting started. Taking this approach, it's very important to bear in mind that no matter what we do, these postulates will remain beliefs. They are not scientific facts. So yes, in science, we have to believe in something before we can really start with exploring. Since the postulates are beliefs, we really need to be aware of the assumptions we make and keep reviewing them. It would be foolish to think we get a perfect system right from scratch after all. And it would be foolish to forget about the assumptions we have made and thus the context we have used to build our future theories. Admittedly, that is hard. All we can really do is to reflect back and see whether we are making progress, whether we are getting closer to our original goal. So it is time and the generations after us who shall be the judge. This was the case for Galileo and Newton and for any other scientist in the past. In fact, it holds true in the present too and will hold true in the future. We are evaluating and reflecting on the work of past researchers, and future researchers will do the same with our work. But isn't it risky to bet such a large enterprise on a set of chosen beliefs? Sure. This is why we should work in a team, decide together, critically evaluate each of our ideas and proposals. This is also why we need to be aware of our assumptions and repeatedly reflect. That should help, hopefully. And yes, taking risks and being ready to fail and learn, that is the job of an explorer. That is unavoidable when we depart into the dark to research and discover something about our universe. Let's put this idea on our mind map. Now let's remind ourselves that when formulating our postulates, we should not overcomplicate things. Let's keep our assumptions simple and in agreement with our past and present experience. Okay, now we understand what to do and why we do it. What set of postulates would you propose to help us overcome the obstacle of trying to understand the universe by being part of it and the resulting questions? Remember to post and discuss your ideas in the comments below as well as on Discord. I think the first postulate should address the questions, what can we know? Based on our original problem, we want to believe that there are laws in the universe and we can know them. Moreover, we believe these laws to be independent of us. They exist independently of us, or whether we are looking at matter or not. For example, whether I drop a pen or you drop a pen, we shall believe that the pen's motion will obey the same laws. But isn't that obvious? Well, if we try that out, then we can indeed see that this is the case. This makes our postulate a justified belief. But is it necessarily true for every pen, anywhere in the world, and maybe on the moon or every planet as well? Has it been true in the past and will it remain true in the future? The answer is that we don't know. But if we have found the fundamental law of motion of the pen, we want to believe that it is universally valid. Hence our first two postulates. First, there exists a universe we are part of, but it exists independently of us. Second, there are fundamental laws in the universe. We can know them and they are universally valid, no matter where and when in the universe. In the next step, we need to answer the question how we can come to know these laws. This is very tricky due to the fact that we are part of the universe again. We obviously cannot simply exit the universe and observe it from the outside, whatever that would mean. But we have a way. Even though we cannot exit the universe, we can think about the universe externally using our mind. We can imagine it and build a mental model. This is where our use of theories comes in. But how can we make sure we just don't invent some fantasy theory about the universe, say that our whole world is just in a locker of another universe, like in the Man in Black 2 movie?
Novellino. Wow!
One way to help us reason about our theory is to use mathematics. Yes, mathematics allows us to keep our reasoning objective and reduces bias. But it is not sufficient to throw some sophisticated theories and mathematics around, as beautiful as they might be. The theory needs to be related to our universe. This is where physics is fundamentally different from mathematics. But maths can help here too. We can use it to make prediction based on our theory. Of course, this only works if the theory has been designed in a particular way to allow this. Something to bear in mind. So, making predictions allows us to test our theories. But how? Are we not just running into the same problem of us being part of the universe? How can we test the theory independent of us? Are we not going in circles again? There is a way out of this one. Let's get inspired by Galileo. Apart from describing the laws of the universe in terms of mathematics, he also proposed a method how to test them. Use controlled experiments. How does that work? How can that work? And do we need to make more assumptions to justify this? Give it a think. Firstly, if we have truly discovered a law of the universe, it should be reflected in how the universe works and the observations we make. For example, if we find the law of motion of my favorite example of a falling pen, we should see that pens tend to follow this law. I say tend because we cannot assume there is just one law acting in isolation, but various laws acting in concert. We need to make sure to control the environment to account for this. This allows us to see that particular law in action as predicted by our theory as best as possible. Say we have tested our theoretical prediction in a controlled experiment successfully. Have we proved the theory right? Justify your reasoning. Most certainly not. We have only shown that our theory is not wrong. An experiment cannot prove a theory right. Why? Think about it. You have only tested it in one place at one particular time. So how can you know it holds everywhere and at any time? Sure, you could test it in various places and by different people, and you should do that. But you can never test if it holds everywhere in the universe and at all times. The more controlled experiments we run that confirms various predictions of our theory, the more confirmation bias we have that our theory is right. But since we are all part of the universe and can only ever have a limited amount of experience, we can never be 100% sure that it is right. Yes, you could be bold and just claim that the theory is right, but it might be better to be more careful here, so that we do not turn blind to evidence showing us the contrary. Or to replace that with our analogy of finding a path through the jungle. Say one of us has observed the nature around us very carefully and comes up with a proposal which way to go. The longer we follow the proposed path successfully without running into a swamp or crocodiles or a huge river that we cannot cross like before, the stronger our belief will be that the path is right. But we will only truly know once we are out of the jungle. We could end up running into a dead end at any point in time. Now, being out of the jungle would mean having figured out all the fundamental laws of the universe. But since we cannot leave the universe, by definition actually, this is why we can never be sure we have reached our goal with absolute certainty. In fact, physicists have been misled like this in the past. After Newton has established his laws of mechanics, the theory remained successful for more than 200 years. You can imagine what strong confirmation bias that must have been, and how difficult it was for the generation of physicists at the end of the 19th and beginning of the 20th century to come to terms that they have discovered experiments that cannot be explained by Newtonian mechanics anymore. Yes, this was the advent of quantum mechanics and general relativity. So how is our method of combining a theory written in the language of mathematics together with testing it using controlled experiments going to help us discovering the fundamental laws of the universe? Your turn. Let's hear your ideas. It seems a bit hopeless indeed. If we reflect critically, then this seems much more likely to happen. Our theories will be really just models and hence approximations of the infinitely complex universe. Experiments will help us to recognize that flaws in our theories and develop better ones. Ultimately, all the theories will just remain approximations though. So how can we figure out the fundamental laws of the universe? Can we? Remember the importance of teamwork we have realized before? Let's think about the progress on a much wider scale across multiple generations of researchers. We will develop a bunch of theories. Each one will capture some aspects of the fundamental laws, at least in the range where it is a good fit and describes the physics of the universe well. Now we, or better, our successors, since we are just getting started here in 1684, remember? They can start looking across the various theories and study which concepts and laws stay the same. These laws are the only ones they might want to believe in as being the fundamental laws. Will they ever know for certain which laws are fundamental? Well, not according to our method. So, can we have a justified belief that this method is going to bring us closer to the fundamental laws of the universe? In 1684, probably not. And yes, it is a bet. But if we jump back to the present and reflect back on the past 400 years, this method has been pretty successful. It has worked really well. Still, reflecting on it, we can also see that it might not be the most effective or most efficient framework. So it is worthwhile to keep thinking about and maybe come with a better one. Anyhow, it does provide a good starting point for our enterprise for now. So let's make this our third postulate and write it down. Let's summarize what we have learned in this session. We started with formulating our aim to discover the fundamental laws of the universe, following in the footsteps of Galileo Galilei. In our first step towards that goal, we have learned and applied some problem-solving strategies to break down and tackle complex problems. Like 1. The method of Socratic inquiry, which was us constantly asking and discussing probing questions to break down a problem, reflect on, and deepen our understanding. 2. Using a mind map to help us develop and keep track of our thoughts while breaking down a problem. 3. Prioritizing the questions that help make effective progress and working from simple to more complex. 4. Bookkeeping of tangential questions and interesting ideas for future research in our personal knowledge management system. You've seen that here and here. 5th, the importance of teamwork and that physics research is fundamentally a human enterprise across generations. This also means we need to study the past to understand the present and then build the future. 6. The need for making assumptions in form of justified beliefs and keeping track of them, as well as reflecting on our progress. In the next step, we have created a philosophical framework to help us getting started with our research. It is based on these 3 postulates. Firstly, there exists a universe which we are part of, but which exists independently of us. Second, there are fundamental laws in the universe. We can know them and they are universally valid no matter where and when in the universe. Thirdly, to uncover the laws of the universe, we will formulate theories and mathematical models of the universe. The predictions of the theories will be tested in repeated controlled experiments. By repeatedly falsifying and improving our theories, We believe to gradually discover the fundamental laws of the universe, thinking across them. You might have noticed that many details have been left unmentioned and need to be clarified. But the vagueness also leaves us a way out to make things precise later when we have arrived at a better understanding. We just cannot expect to get everything perfect right from scratch. That would just hold us back. To be able to explore the many ramifications of our postulates, or maybe even proposing other systems, we need to discuss and think this through together. So make sure to think about and question what has been said in this session. Join the discussions in the comments below or on Discord. If you have different ideas or have come to different conclusions, that's great. Develop them further. Also, think about the consequences of the three postulates we set out. What will count as a theory in our sense and what won't? What will be important ingredients of a mathematical theory so it can be applied to our universe? What is it that makes a physical law fundamental? Are there non-fundamental laws? And if yes, how could we distinguish them from fundamental ones? And remember our stipulation that the more complex can be understood in terms of the more simple? Is that really the case? Or are there qualitative leaps? For the context, it is important to note that I have been steering in a certain direction here. The principle of falsifiability of a theory and the emphasis of both theory and experiment is at the heart of Karl Popper's philosophy of science and based on his philosophy of critical rationalism. Popper has been one of the most influential philosophers of science in the 20th century. You can learn more about him and his influential book, The Logic of Scientific Discovery, by following the links in the descriptions below. Just note that the framework we have built is not detailed and developed enough to be attributed to one particular philosophy of science. We can still utilize ideas from several of them. I do really want to stress the incredibly importance of philosophy here. Without philosophical considerations, we would not be clear about our assumptions, and thus the intellectual cage we have built for this whole enterprise called theoretical physics. Our departure into understanding the universe would be very much unreflected and ad hoc. But does that even matter as long as we are making progress towards understanding the universe? Yes, it does. In particular, when we start thinking about applying physics and its methods to all sorts of things. For example, living organisms and in particular, the human mind. Let's consider problems like studying the mind in cognitive neuroscience. Based on our assumptions and approach, we would be very much inclined to believe that what we refer to as mind is an emergent phenomenon based on the physics of the billions of individual neurons acting together. Hegel, for example, says that the whole is more than the sum of its parts. This means that our mind cannot be fully understood by looking at the individual neurons alone. The neurons acting together produce something that is qualitatively different from their individual traits. Marcus Gabriel, a contemporary philosopher, also argues that fundamental laws of the universe, which would explain the universe as a whole, do not exist. In his philosophy of a new realism, he postulates that a thought exists as well as the planet Earth exists. However, they have different forms of existence, of course. Which form of existence you consider depends on the field of sense. As there are infinitely many fields of sense, there are infinitely many aspects of existence. I think Gabriel would agree with Hegel, but due to different reasons. He would also reject the idea that you can understand the human mind entirely by looking at the individual neurons. How would physics look like if we tweak our postulates and philosophical foundations, maybe adopting a more of Hegel's or Gabriel's philosophies? You can learn more about Gabriel's philosophy by watching one of his talks on why the world does not exist, linked in the description below, as always. Let's turn to the problems for this session. There are 3. Problem 1 and 2 will be discussed in the review session in a week's time, and I'm curious to learn what you will come up with for problem 3. All subscribers should use the problems discussion channel on Discord and create threads to discuss their answers and submit resulting questions you would like me to address in the review session. Everyone else is invited to discuss the questions in the comments below or in the physics channel of the PhysicsBeyond community category on Discord. Please use threads as well to keep it organized. Problem 1 is about Aristotelian physics. Aristotle is yet another very influential ancient philosopher. He proposed a scientific method to uncover the truths of the world very similar to ours. First, you start by making observations. You infer general principles from the observations you have made. Third, you deduce further observations you should be able to make based on the proposed general principles and see whether they agree with actual observations. Fourth, repeating the cycle will help you gradually refine and improve the general principles. Using this method, Aristotle arrived at the following conclusions about the physics of our world. Firstly, we have to distinguish between the physics of the Earth and the physics of the sky, or terrestrial and celestial physics, as he used to call it. On Earth, all objects are naturally at rest or fall to the ground. If you interact with them and transfer energy, they will start to move until that energy is depleted. Once the energy is depleted, they come back to rest. Third, in the sky, on the other hand, objects move constantly and never come to rest. That is their natural state of motion. Are Aristotle's conclusions sound according to his own method? If no, why not? If yes, how would they follow from applying his method? Would he arrive at the same conclusions if he had followed the method we have proposed? What are the similarities? What are the differences? For the second problem, let's jump back to our present time. Looking back at the various theories that have been proposed in physics up to now, what would you say are good candidates for being fundamental laws of the universe? The last problem is a very open-ended question where I want you to reflect on the method we have proposed and discuss how it could be improved. Or should we change it entirely, maybe? It would be great to look at the different philosophers like Hegel or Gabriel or the philosopher of your choice. Let's think how the scientific method could be tweaked or extended based on their philosophies. Oh, that was a long and super hard session. Well done for making it through to the end. I'm sure your heads must be spinning, thinking hard about so many tough questions in such a short time. Please hit the like button if you liked this video or the idea of physics from a researcher's point of view. This feeds the algorithm and helps more people like you to find this course. If you wish to participate in this course, hit the subscribe button so you know when the next video session will be released. If you wish to support the community work PhysicsBeyond is doing, like our Beyond Research program, for example, please subscribe to the Researcher's Point of View course by becoming a member on Buy Me a Coffee. Or support us with a small donation. The link is below. Many thanks. If you have just joined the session, please make sure to check out session 00, which explains the course format to you and how to get the most out of it by using the support available. Now, if you want to see a pen drop in slow motion, I have a link for you in the description below. If you want to learn more about the amazing physics of falling cats, you should absolutely watch Destin's video from Smarter Every Day. Finally, if you want to learn more about the history of physics, you should definitely check out Katie's amazing channel. All the links are in the description below. Thank you for watching until the end, and I shall see you in session 02, where we will continue our intellectual journey into the realm of theoretical physics.